Hi everyone. Previously we formalized the idea that physical observables are linear operators in quantum mechanics. We found that the definite states of that observable correspond to the eigenvectors, and the definite value that we would measure in that state corresponds to the eigenvalue. In this episode, we're going to put everything together to intuitively understand the Born rule, which tells us how to determine the probability of a particular outcome. Let's start by familiarizing ourselves with some previous results. We found last episode that the eigenvectors of an observable have to form an orthonormal eigenbasis. So, we have a position and momentum eigenbasis, which are continuous in normal circumstances, an energy eigenbasis, and so on and so forth. So, for our arbitrary quantum state, we can expand our state in terms of a linear combination of these eigenbases, which represents being in a superposition of all those values for the observable. If the continuous linear combinations for momentum and position are unfamiliar, I recommend refreshing with Chapter 2 of the series. Note that this is the same quantum state in all of these expansions. We are just expanding the state in a different basis. Let's take a closer look at the energy eigenbasis expansion. Given that we have expanded our quantum state in terms of the energy eigenbasis, how would we use this to find the probability of measuring an energy of, say, E4? To begin tackling this problem, let's look at the case where we have a two-dimensional vector space. Let's assume that 1, 0, and 0, 1 are our energy eigenbasis vectors, corresponding to energy values 2 and -2 respectively. Intuitively, we would hope that a quantum state really close to 1, 0 would have a really high probability of measuring an energy of 2, since the states are almost the same. Likewise, if the state were really close to 0, 1, we'd expect a really high probability of measuring an energy of -2. How do we quantify this idea? Well, if our state is close to a basis vector as shown, then the component of our vector along that direction must be large. So in this example, the state has a large component along the 0, 1 direction. Therefore, our conclusion is that it seems intuitive that the larger the component along a certain eigenvector, the larger the probability of getting that particular outcome. So let's follow our intuition. To start finding the probability of getting an energy of, say, E4, we want to find the component of our quantum state in the direction of the E4 eigenvector. You may remember that the way we calculate the component, also known as the projection along a certain direction, is to take the inner product with the unit vector in that direction. Note that the order of the inner product matters. We are starting with the psi-ket and projecting by applying the E4 bra. Now we expand psi, and then distribute the inner product. Since our eigenbasis is mutually orthogonal, the only non-zero inner product is E4 with itself, which just gives us 1. Therefore, the component along E4 is just the corresponding coefficient. We've hinted at the idea that the coefficients are related to probability, but now we see why. The coefficients intuitively represent how close we are to that eigenstate, and therefore how probable it is to measure it. So, given an eigenbasis expansion, we want to relate the probability of getting a certain value to the corresponding coefficient of that value. Our first guess might be to take the absolute value of the coefficient. This captures the length of the component while taking care of the case when it may be negative. But remember, we could very well have complex number coefficients, and when we derive the Schrödinger equation, we'll see that we need imaginary numbers. So we can generalize this absolute value to the magnitude of the complex number, which should still capture the length of the component. Now, this is a really good first guess. So good, in fact, that physicist Max Born also initially thought that something like this must be the probability, only later changing it to the correct answer. So, why is this wrong? Let's try and get some intuition into why this leads to some problems. For simplicity's sake, let's assume the coefficients are real numbers, and that we are in a 2D quantum vector space. Therefore, our eigenbasis expansion only has 2 terms. We postulate that the probability of measuring an eigenvalue is equal to the absolute value of its coefficients. Remember that the sum of probabilities over all possible outcomes must be equal to 1. This gives us the condition that the sum of the absolute values of the coefficients must also be equal to 1. Since we are assuming a 2D vector space, we only have 2 outcomes to worry about. Note that this condition actually implies that the total length of our quantum state is not necessarily equal to 1. For example, let's say both eigenvectors have an expansion coefficient of 1/2. Our probability condition is satisfied, but the length of the vector is now 1 over the square root of 2. This isn't necessarily a problem in and of itself, as long as the total probability condition is satisfied. But this introduces another issue. Let's go to the 2D plane to see what that is. Here I have a particular set of energy eigenbasis vectors, E1 and E2, shown in blue. Let's say our quantum state points along 1, 0. In this basis, we can expand our state as follows. Note that the absolute coefficients add to 1, so our total probability condition is satisfied. Now, looking at a different observable, let's say the angular momentum eigenbasis vectors are L1 and L2, shown in red. When we take our same quantum state and expand it in the angular momentum eigenbasis, we get the following. Notice, the absolute coefficients no longer add up to 1. This means that when working in this basis, we need to rescale our quantum state in order for the coefficients to still be probabilities. After rescaling the quantum state, we now get coefficients whose absolute values add up to 1. So depending on which observable eigenbasis expansion we're working with, we have to vary the total length of our quantum state. But this sounds strange, doesn't it? Before measuring energy, our quantum state has a certain length, but before measuring angular momentum, it may have a different length. So what's the actual length of our quantum state before we measure anything? And why should it depend on what basis we're working in? If we assume a particle is represented by a single quantum state, then we have an issue. So how do we solve this dilemma? Well, the first thing we should do is question our probability function assumption. So let's instead work with some unknown probability function f. We want this probability function to satisfy two conditions. First, no matter what probability function we choose, when we add together all the probabilities associated with each outcome, it has to equal a constant 1. Second, we'd ideally also want one that ensures the length of the quantum state stays constant in any basis, remembering that the length squared of our quantum state is calculated by the sum of squares of the coefficients. Here we write the constant as k squared to enforce that it must be positive. So what probability function will satisfy both of these? It may seem hard to find f given only these two conditions, but let me run you through what goes through my head when faced with a problem like this. In general, when I'm tasked with quote-unquote solving for a function like this, my mind immediately jumps to finding a differential equation that f must satisfy. In the same way that we use normal equations to solve for numbers, we almost always use differential equations to solve for functions. So our overall strategy is that we should see what these two conditions imply about the derivative of f. Before doing that, let's take a second to analyze the second condition here to see how all the coefficients relate to each other. First, what values can we choose for c1? Well, the only real constraint we have is that c1 squared has to be less than or equal to k squared, since otherwise the left-hand side would be bigger than the right. In other words, the choice for c1 is any number between negative k and k inclusive. If we choose c1 equals negative k or k, then we can see that we need to set all other coefficients equal to 0 if we still wish to satisfy this condition. Let's look at the case where we don't choose negative k or k, and therefore don't immediately constrain all other coefficients. So let's instead choose a number a within this range. Now our condition looks as follows, and we can move a to the other side. Now, what values can we choose for c2? Well, our logic stays the same. We can choose any real number for c2, except now we just need to make sure that c2 squared is less than k squared minus a squared. In other words, the choice for c2 is any number between these two values inclusive. Again, let's assume we stay away from the boundaries of this range and choose a value b for c2. Like before, this gives us the following equation. And we can continue this process for each c, getting a range of values for c3, c4, all the way down to Cn. Once we get to here, what values can we choose for Cn? Well, now we don't really have a choice anymore. Cn can only be plus or minus the right-hand side. Once we've chosen all the other coefficients, Cn is always constrained to 2 points, or 1 if the right-hand side is 0. So, why am I making a big deal out of this? The main takeaway is that most C are basically independent of each other. As long as we stay away from the boundaries, choosing a C only tells us what range of values the other C can take, but they are independent otherwise. The exception to this is the last C, which will always be constrained to one of two numbers or 0. This might seem like a weird overall takeaway, but trust me, this is actually the key to finding F. Last thing, let's establish one more property of F that we'll need to use. If we believe that the probability of an outcome only depends on the size of our projection along an eigenvector, then the associated probability shouldn't change if the projection is pointing along the eigenvector or against it, as long as they're the same size. Mathematically, a backwards pointing projection manifests as a negative coefficient. So, in other words, our intuition tells us that F shouldn't care if the coefficient is positive or negative, i.e., F is an even function. Hopefully you see why this makes a lot of sense. With that, let's finally do some mathematical heavy lifting to find F. Let's start with the first condition, and let's single out the term with the last coefficient. Now, we can use the second condition to solve for Cn, and then we can plug this into the second term here. Now, here we use the fact that F is an even function to get rid of the plus minus. Now let's follow through with our original idea and see what we can learn about the derivative of F. Since C1 is an independent variable within its range, we can take a derivative on both sides with respect to C1. And since the right-hand side is a constant, we get 0 on the right. Here is where we use our important takeaway from earlier. Remember that all the Ci are independent except for the last one, which we already pulled out of the sum. They only affect each other in the range they can take on. So for any Ci that isn't C1 inside the sum, varying C1 doesn't really change that Ci. They're independent. So all the terms in the sum are equal to 0, except the term with C1. In the term we pulled out, we simply use the chain rule to take the derivative with respect to C1, where we again use the fact that the Ci don't directly depend on each other. This is a subtle argument, so take some time to really understand what we did. Rearranging this equation to get the loose C1 terms all on the left, we get the following. Now, there's nothing special about C1. We could have done the exact same thing, except now we take a derivative with respect to C2. All the same arguments would apply since C2 is just as much an independent variable as C1, and we'd get the same relation, except with C2 on the left. But note, these two equations have identical right-hand sides. So we have that these two quantities must be equal to each other. Now, isn't this sort of a funny relation? On the left, we have all independent variables C1, and on the right, we have all C2, another independent variable. To see what this implies, let's take a derivative with respect to C1 on both sides. Let's now think about what the right-hand side derivative is asking. It says that we should vary C1 and see how much the value in the parentheses correspondingly changes. Well, as long as C2 is within the allowable range, it doesn't change at all. It's free to be what it wants even if C1 changes by a bit. In other words, this derivative must equal 0, since C2 doesn't directly change when C1 changes. This is another really subtle argument, and it's the key to finding F. So take a second to make sure you really understand why we were able to say that the right-hand side must be 0. If you've ever taken a course on partial differential equations, this is the same argument used in the separation of variables technique. Once we do this, we can take a step back and look at what we have. This is it. This is our differential equation for F. Again, there's nothing special about C1. We could have done this with any C. So let's replace the argument with a generic coefficient C. Now let's carry it home. The overall derivative on the left equals 0, which means that this must equal some constant lambda. And we can rearrange to get this. We can now integrate both sides one more time, and we get the following, where we remembered to add a constant of integration, mu. Isn't this exciting? We finally see that the probability function must depend on the square of the coefficient. All that's left is to find the constants of integration. To do this, let's first think about what f of 0 should be. In other words, what should be the probability in the case that the corresponding eigenstate has 0 coefficient? Well, in this case, our quantum state has 0 component along that eigenstate. So it should be intuitive to expect that the corresponding probability is 0. So we have f of 0 is 0. And this allows us to conclude that mu must also be 0. To figure out the other constant of integration, let us look at condition 1 again. Let's assume that C1 takes the maximum value k, and therefore all the other coefficients have to be 0. Since we showed that f of 0 is 0, this implies that f of k must equal 1. Plugging in this condition will tell us that lambda must equal 2 divided by k squared. And therefore we have our final result. Given the eigenstate expansion, the probability associated with that eigenstate must be equal to the coefficient squared divided by k squared, which remember is just the length of our quantum state. Now, note that we have some freedom with k. Our only condition was that we wanted our quantum state to have a constant length in any basis, but we have the freedom to choose what that length is. As is conventional, it's simplest to choose that our states should have magnitude 1, and hence k equals 1. Lastly, if we have complex coefficients, then it makes sense to generalize this to the complex magnitude squared. So we have the following magnificent result. If we take all quantum states to have length 1, then the measurement probability associated with a particular eigenstate is equal to the amplitude squared of its coefficient when we expand our state in that eigenbasis. Also remember that we found that we can find the coefficients using the following inner product. So we can state the result as follows. This rule for probabilities is known as the Born rule. Many quantum textbooks declare it as an axiom, but hopefully you see why it shows up in our mathematical model. Although our derivation focused on intuition, there is a rigorous theorem that establishes the foundation of the Born rule, known as Gleason's theorem. I won't delve into the full rigorous theorem, but I encourage you to look into it if you're interested. I will mention one thing though. Gleason's theorem is only valid for vector spaces of dimension 3 or greater, and we can see why this is true from our own derivation. Remember that the pivotal step in our derivation was the following, where we found an equation relating two independent coefficients. How many dimensions do we need in order to have at least 2 independent coefficients? At least 3. If we had only 2 dimensions, then we'd only have 1 independent coefficient, because fixing one would immediately fix the other to plus or minus something. In a weird way, we sort of have too many constraints in 2 dimensions. We need a little more wiggle room in order to find out what f is. Although our derivation and Gleason's theorem only holds in 3 dimensions or greater, it just so happens that the Born rule still applies in 2-dimensional quantum vector spaces. So, at the end of the day, nature still supplies the Born rule as a sort of axiom, but that doesn't stop us from doing our best to understand its origin. Now, we have so far been working with discrete eigenbases, but what about continuous ones? For example, remember that position has a continuous eigenbasis, and therefore our eigenbasis expansion looks like the following. So what's the probability density of getting a particular position? Well, given the Born rule, we know that the probability density of position is equal to the squared magnitude of the coefficient in front of the eigenstate. Look familiar? I told you to take my word for it before, but hopefully now you see that this coefficient function really is the wave function. Now, what does it have to do with waves? Again, be patient until we derive the Schrödinger equation. Now that we know how to calculate probabilities, I want to leave you with a problem to test your knowledge. You may have seen that in quantum mechanics, we calculate the expectation value, aka the average, of an observable with the following expression. I encourage you to try and show that when you expand each ket in the eigenbasis of the observable, this reduces to the common expression for the expectation value. If you got that down, see if you can do it for an observable with a continuous eigenbasis, like position. It should reduce to the common expression for the expectation value given a probability density function. With that, we've basically derived the framework for our mathematical model of quantum mechanics. We've covered a lot of mathematical ground so far, so let's recap everything we've derived in what I call the quantum prescription. In this model, a particle is represented by a vector in a Hilbert space, also called a quantum state. We chose a special notation for this vector that we call a ket. This quantum state holds all the information about the particle, including the possible positions, momenta, energies, etc., as well as all the associated probabilities of measurement. Physical observables, on the other hand, are represented by linear operators in our vector space. The eigenvalues of the operator tell us all the possible values that we could get if we measured that observable. The corresponding eigenvectors represent definite states, in which the particle 100% has that value. To figure out the probabilities for a particular observable, we first expand our quantum state in a linear combination of that observable's eigenstates, which could be discrete or continuous as shown. The probability or probability density of measuring a particular value is equal to the magnitude squared of the coefficient in front of the corresponding eigenstate. This is the Born rule. When we measure a particular quantity, we will randomly get one of the possible values, according to its probability. Once we've made the measurement, we now know that this particle 100% has this value. Therefore, we know that it must now be in this definite eigenstate. This is known as quantum state collapse, since the act of measuring necessarily collapses the particle into a random definite eigenstate. The particle then goes on and evolves in this new definite quantum state. And that is our linear algebraic framework for quantum mechanics. As you might expect, the precise mechanism for quantum collapse is a very mysterious and highly debated part of quantum mechanics. For now, I recommend you simply understand how it is mathematically modeled. For the rest of the series, we're now going to focus on better understanding the details of this framework, such as Hermitian and unitary operators, and also deriving time evolution through the Schrödinger equation. Thank you so much for watching. As always, if you have any questions, feel free to leave them below. Hope to see you next episode, where we'll finally dive into Hermitian operators.